Welcome. In this video, we're going to talk to you about how we can add and subtract when our numbers are in scientific notation. Our first example here, we see 4 times 10 to the 7th, and we want to add that with 3 times 10 to the 5th. We're going to first look at our objectives today. Our objectives, the first one told us to understand there are 2 different methods that we can use to add or subtract numbers when they're written in scientific notation. The first method, option 1, is to convert the numbers to decimal notation or regular numbers and then add those up using the algorithm or the regular way we've always added. The second option is to transform the numbers so they both have the same power of 10, and then there's a nice shortcut where we can add or subtract the coefficients and the power of 10 would just stay the same. Let's take a look at what we mean. In this example, 4 times 10 to the 7th plus 3 times 10 to the 5th, the first thing to note, the powers of 10 are not the same. This is 10 to the 7th, this number is in the 10 millions. This is 10 to the 5th, this number is only in the 100,000s. We're not going to just be able, because of order of operations, PEMDAS, we can't just add the coefficients together, we can't just multiply or add together the powers of 10. Method 1 tells us just switch these over to regular numbers. So we know that 4 times 10 to the 7th is actually just 4 times 7 copies of 10. And if we put our commas in, or if we understand what 10 to the power of 7 means, we know that makes 40 million. 3 times 10 to the 5th, we can convert that to a regular number as well. 3 times 5 copies of 10 would just add 5 zeros to that number. We also might know that 10 to the 5th, right below 10 to the 6th, is going to be 100,000s. Now we need to add these two numbers together. The key when we add with the algorithm is to line up the commas and the place values so the decimal point lines up, the commas line up, then the addition is pretty straightforward. 40 million plus 300,000 ends up making 40,300,000. We put that into scientific notation. Decimal points right here, moves 3 places, 6 places, 7 places, so 4.03 times 10 to the 7th. Method 2 would ask us to try to get the powers of 10 so they were equal to each other. 4 times 10 to the 7th plus 3 times 10 to the 5th. Well, I know 4 times 10 to the 7th, we could really rewrite that, 4 times 10 to the 7th, as 400. If we take 2 of the copies of 10 and multiply them with 4, 4 times 10 times 10 is 400, and that would leave us now with just 5 copies. I wanted to get down to 10 to the 5th, so I took 2 of those powers of 10, multiplied them with the 4, turned it into 400. Now that we see both of these 400 times 10 to the 5th, 400 copies of 10 to the 5th, plus 3 more copies of 10 to the 5th, that just ends up being 403 copies of 10 to the 5th. Now that's not in scientific notation. We would need to move the decimal point 2 places to the left. 403 could become 4.03. And when we do that, because the decimal point moved 2 places to the left because we divided by 10 twice, we need to balance that out, add 2 more copies of 10. And we realize both of these methods give us 40,300,000, or 4.03 times 10 to the 7th. You can pause here and work on problem 1 and 2. If you keep following the video, we're going to look at negative powers of 10. This will help us when we get to problem 3 and problem 4. Now we're looking at negative powers of 10. 3 times 10 to the negative 2nd minus 7 times 10 to the negative 3rd. Again, method 1 would ask us to switch these to regular numbers. So just like we did with the positive powers of 10, we would switch both of these over to decimal notation. 3 times 10 to the negative 2nd means I move the decimal left twice, or divide by 10 twice. That gives us 0.03. 7 times 10 to the negative 3rd, when we switch that, 0.2 zeros, then a 7 because that decimal point moved 3 places, 1, 2, 3 to the left. We're going to be subtracting here, and remember again, the key when we subtract or add with the algorithm is to line the decimal points up. Here 0.03 is the same thing as 0.030. Now I just see that when we do this math, When I make the subtraction, 30 minus 7 is 23, so I'm going to get 0.023. If we write that in scientific notation, 2.3 times 10 to the negative second, because we see the decimal point needed to move 2 places to the right. That'd be multiplying by 10, so to balance that out, 2.3 times 10 to the negative second. If we used our second method, we would need to get these powers of 10 equal to each other. 3 times 10 to the negative second is bigger than 7 times 10 to the negative third. We know that because it's divided by fewer copies of 10. So what I'm going to do here, 3 times 10 to the negative second, I'm going to switch that over to 10 to the negative third. I want it to match up the same power of 10 as the one over here. If I bring in another negative power of 10, I divide by 10. This has to be balanced out by getting multiplied by 10 in the coefficient. 30 times 10 to the negative third has the same value as 3 times 10 to the negative second. Now at that point, we'd be able to take the rest of our equation, subtracting 7 times 10 to the negative third, and then we'd see 30 minus 7 leaves us with 23. That's 23 times 10 to the negative third. And then finally, move that decimal point 1 place to the left. That tells us 23 times 10 to the negative third has the same value as 2.3 times 10 to the negative second. Again, two different methods, both arrive at the same answer.